Now we finally get to the good part. We're finally to neutrons. We said that there was an alpha, beta, gamma, and a neutron, and we haven't really talked much about the neutron yet, but the neutron is really cool. If we start talking about the neutron, we know it's inside the nucleus. It has a mass. Its mass is about 1 atomic mass unit, and its charge is 0. It lives in the nucleus. What's really cool is this first thing we're going to talk about is mass defect. Mass defect. And if I was to take a bunch of neutrons, they're all neutrons. 5 neutrons. 4, 3, 2, 1. And then a bunch of protons. I'm going to make, let me start over. I'm only going to make 4 neutrons. 1, 2, 3, 4 neutrons. I'm going to put an N here for neutrons. And I'm going to have 3 protons. Now I could go individually weigh the mass of these protons. Mass of these protons. And I know that I should come up with approximately 3 atomic mass units. And if I was to go then weigh the mass of these neutrons, I'm just weighing them all individually, I would come up with approximately 4 atomic mass units. And I will tell you, you got to take this number really far out, way past the decimal point to get this accurate. But I can see that I have 3 protons, 3 neutrons, and I would have, if I mashed them together into a nucleus, I would have 3 lithium-7. So what you would think is then that the mass of this 3 lithium-7 would be equal to the constituent components mass, the mass of the protons and the mass of the neutrons. But that is not true. Not true. It's weird. The mass of this atom will always be less than the mass of the constituent components. And that is called the mass defect. Let's take a look. The symbol for mass defect. The symbol for mass defect. Mass defect is referred to as delta M. The change in mass that occurs. And if I wanted to determine the mass defect, I take the Z number, the number of protons, and I multiply it times the mass of a hydrogen. Why do we do that? Mass of a hydrogen atom? Well, a hydrogen is 1 proton. Plus, I'm going to take the mass. So this represents essentially the mass of the proton. Plus, I'm going to take the mass of the neutrons all together. So I've got protons plus neutrons mass. Then I'm going to subtract the mass of the atom. And what I'm going to end up with is a difference in mass. That's called the mass defect. They're not the same. The mass of these constituent components was greater than the assembled atom. That's a mass defect. And the unit is in atomic mass units. So now the question becomes, where did that mass go? I had some mass, now I've lost it when I put them all together into the atom. Well, that is a cool thing. That is called binding energy. Some mass was converted to energy, and it was lost. So some mass was lost, it was converted to energy, and that binding energy is the energy that's keeping the atom together. because they were separated. Now they're together, and there's some sort of energy, some sort of nuclear force now that has to hold it together. And it didn't come from nowhere. It was a conversion of some of this mass that initially these constituent components had to energy. So the mass equivalent of binding energy is of the mass defect and binding energy rather are equivalent. Mass defect and binding energy are equivalent. That's weird. So some mass has been converted to energy, and they're equivalent. I said that several times, like a broken record. And there is a conversion that you can use. If you determined the mass defect of an interaction, and you wanted to know what the binding energy of that was, of that interaction, and I know that some mass got converted to binding energy when I created the atom. Here we are. This is a great number we get from a really old smart guy named Einstein. There are 931.5, here's a unit, mega electron volts per atomic mass unit. Wow. So when I take uranium, and I have a neutron here, and it goes into here to uranium-235, and then it splits into some sort of fission fragment here and here, not even counting what else is going on. I've created a mass defect. There's going to be a difference in mass between these constituent components and what started it. And we always know this mass was less, so I can liberate the energy here, essentially. I can liberate this binding energy. And it is generally that energy that I will see is in the form of kinetic energy of these fission fragments right here. They will now, this uranium atom was sitting here fat, dumb, and happy, being left all alone, and then a neutron came in, and it split apart, and I no longer have uranium, and the two pieces that are split are zinging across. They now have kinetic energy. I have essentially allowed some of that binding energy to escape. I've released some binding energy. Pretty cool. That's a useful conversion right there. If I can determine the mass defect of any interaction, then I can determine what the energy is, the binding energy. So binding energy is the energy equivalent of the mass defect. Mass defect is the mass equivalent of the binding energy.